Folks, we're getting ready to do more example problems, and these example problems are going to focus on the carbonyl reactions. And these example problems are great. Don't snarl your nose against the example problems. They didn't do anything to you. They are actually helping you pass the class. So that's how I want you to regard examples after examples after examples after examples. All right, so let's take a look at this reaction and predict what happens. Now, first off, I want you to name them. You should be able to name both of these right now. Yes, that's right. You should be able to name both. So let's take a look at the first one. What type of functional group? Question A. On a test. Hint, 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 hint. What type of functional group is this? C double bond O with the chlorine. Oh, Tracy, this is an acyl halide. You did a great job teaching us that functional group. Ding, ding. That's correct. That's an acyl halide. Okay, name that acyl halide. Well, how would you want it, sir? Well, you can name it IUPAC or you can name it common. You pick it, unless I tell you otherwise. So let's do both. Let's start with IUPAC first. Okay, 3-carbon chain. Prop, P-R-O-P-A-N, drop the E, and add oil. So propanoyl chloride is going to be the IUPAC name. You want the common name? I'll give you the common name too. This is propan, and it's propionyl chloride. There you go. Well, what about the other one? How do I name the other one? That's not a big deal. We've named this too. That's a benzene. And that benzene has an OH on it. You should have memorized those benzene structures. Did you memorize them? Because this is where it's going to test you. And this benzene ring with an OH group, folks, that was phenol. So in this reaction, we are taking propanoyl chloride. We're reacting it with phenol, and we want to know what product is going to get formed, and then we're probably going to end up naming the product, maybe. So how do we do it? Well, we do it just like before. There's no difference. We start with the carbonyl. So in the mechanism, the oxygen, folks, there's your negative. There's your nucleophile. That's the definition. And that nucleophile is going to search and search and search, and it's going to go to the bathroom. It's going to take a clean shower. It's going to primp. It's going to pamper itself. I mean, you talk about the makeup and the cologne and the deodorant and everything else in between, maybe even a new pair of underwear, that phenol is going to put on for that evening. And that phenol is going to go out to the bar, and that phenol is going to look, and it's going to see this carbonyl, and that carbon is involved in an oxygen, and it's going to look at this, and it's going to go, guess what? Hubba hubba, hey carbon, because that carbon is partially positive, and this oxygen is partially negative. That oxygen is more electronegative. That oxygen's more electron greedy. That oxygen's going to suck up the electrons as much as it can. And when that happens, we can show that in form of the mechanism. Those electrons get pushed up to the oxygen because that carbon is going to go, oh yeah, come on, I'll take your number. You can buy me a drink. That's not a problem. And then oxygen gets mad. Oxygen gets jealous, and it says, no, not today. And it pushes those electrons back. When it pushes those electrons back, it forces carbon into a decision. What do you do, carbon? Which one do you get rid of? And it looks at this incoming nucleophile, and it says, well, this is kind of like an O and an R group, right? I mean, because I've always told you, split that hydrogen off. It's like HOH or HOR, and that's exactly what we have here. It's an HOR. This is an alcohol. So it's going to look at the OR group, and it's going to go, you're prettier. And because you're prettier, chlorine, there you go. Bye-bye. See you later. Don't come back unless I get hard up again. And then carbon will come around and say, hey, chlorine, you want to kind of make this work again? Chlorine, don't fall for it. If it happens one time, it's going to happen again. Don't get used and don't get abused. That's what my advice is to the halogens. So with that said, folks, there's the mechanism of this reaction. That wasn't hard. That wasn't difficult. It's everything that we've talked about so far. So instead of chlorine on here now, that chlorine is going to be substituted through the nucleophilic acyl substitution reaction, and what we end up with is this oxygen that has this benzene ring on it, and of course that oxygen is also going to bring the hydrogen to the table in the beginning. So that oxygen realizes it's got to dump something too in order to make this work. So that oxygen says, hydrogen, pew, off you go. To the road, hit the road, Jack, and that neutralizes that oxygen back out, and there's our product. Where does that H go? Well, that H is going to fly off, pew, just like the chlorine flew off, pew, and this H and HCl, they kind of have an attraction, don't they? So it looks like these reactions could generate a little bit of acidic environment. And sometimes we want to neutralize the acidity of the solvents that are getting generated in these organic reactions. And that's why sometimes we'll go through these moments of looking at these reactions in the laboratory and we add certain ingredients along through the ride. And this is one of the reasons we want to kind of neutralize that acid content out of here. So down below is the product of this reaction. If I asked you for the functional group, what type of functional group is this? This is a C double bond OO, so that is an ester. So I can at least identify the functional group, and that ester group we can name. So if you go back and kind of review the nomenclature of esters, it's basically going to tell you name the group on the O first. Well, that's a benzene directly connected to the O, and that benzene directly connected takes the name of phenyl. There is no carbon middleman, right? It's directly attached to the oxygen. So now that we've named that piece, we have to go back and name the long carbon chain. That long carbon chain here is going to be propane. Drop the E and add O8 to the name. So phenyl propanoate, or I could actually also call it phenyl propionate. So if I wanted to give you a common name, it's propion, and I drop the O and I just put 8 instead of O8. So phenyl propanoate or phenyl propionate. Either one of those, tomato, works for me unless I specifically tell you to give me one or the other. Folks, there you go. There's a reaction. You know, this doesn't really take any kind of studying because I could hit you with a number of different reactions that are thrown your way. And as long as you go through the mechanism, as long as we think these things through, organic chemistry is not memorization. Organic chemistry is learning. We're learning a procedure, and then we apply that procedure to whatever is in front of us. We have to critically think these problems through. So, you know, get your critical thinking hats on, because a lot of times we just don't wear any type of hat, much less a critical thinking or a common sense hat that's out there. All right, so let's take a look at another one. Here's another reaction. And I'm going to say, name the functional group. Okay, so that's going to be part A of the problem. So name the functional group here. Oh, well, this is an acyl halide. All right, I know that. It seems like that's all we've been using. That's okay. We'll quickly get out of this. So if this is an acyl halide, then I could tell, name it. Okay, so we'll go through and name it. 4 carbons in a row. 1, 2, 3, 4, right? So this is a butane. Drop the E, and what do? We add oil. So butanoyl, and it's a chloride. So butanoyl chloride. Or we could call this butyryl chloride. That's the common name. Butyr with a YL. And then it looks like we're going to take butanoyl chloride and we're going to react this with water. And we want to know what happens. Okay, so here we go. Same old story. I mean, that's just life, right? It's the same old story over and over. All right, so here we go. 4 carbons. That doesn't get touched. It stays the same. That is what it is. There you go. So I told you over and over, look at this water, back in Chemistry 251 if you had me as well. This is an HOH. I want you to think of it as that way. The oxygen's the electron carrier, the oxygen is the negative, the oxygen makes it a nucleophile. So, oxygen cleans itself up, puts on a new dress or a new suit, maybe a brand new spanking watch and a ring, and it goes all out of the house fancy. And it goes into the bar, and it says, hubba hubba, carbon, here you go. And that carbon says, oh yeah, come on over. I mean, you know, you're kind of ugly, but you're prettier than that chlorine maybe, based on that nucleophile chart that I carry around in my pocket. So that carbon decides to shove those electrons up to oxygen, and oxygen says, you're going to shove them back. And that carbon says, okay, now I've got to figure out what to do. I've got too many bonds. Which one do I get rid of? And it's going to get rid of the chlorine, because that chlorine is uglier than the water. And we know that because I've referred to the chart. I keep referring to the chart. Hint, hint, hint. You're going to have to use the chart over and over. So if I do this, that chlorine leaves, and then what comes on is an OH with a hydrogen. Remember, I always do this first just to kind of keep in your head that this is the proper order of the mechanism steps. Now, once this goes on, oxygen realizes it's got too many bonds. It's got to fix itself. So oxygen decides to get rid of that positive charge. It wants to be neutral. And the way it does it is to get rid of the hydrogen, and that hydrogen can be pulled off from another water molecule. That hydrogen can be pulled off maybe from a chlorine. That hydrogen can be pulled off, bottom line, with the solvents or in the environment that this reaction is taking place in. So that hydrogen gets removed, and what do we have left? What type of functional group have we produced? Oh, well, Tracy, you told us C double bond OOH. I know that. That's called a carboxylic acid. Well, good for you. Ding, ding. You just got some more points on a question. And now I'm going to say, now name it. How would you name this? Okay, so the way that we name it, longest carbon chain, butane. Drop the E, and what do you add? Oik. So butanoic acid. That is what I have made in this reaction. Well, if you didn't want to use butanoic to be prim and proper with IUPAC, you could call it a common name. And this common name is going to be butyric acid. Again, same prefix we've always used for a carbon chain, and we just add ic onto the end. Butyric. Butyric is the smell of rancid butter all over again. So, if you ever want to get back at an X, the only thing that you have to do is get some butanoyl chloride from our lab shelf, because we have it all the time, mix it with nothing more than just a little bit of water, and you will form butanoic acid or butyric acid, and that butyric acid will take on the smell of rotten eggs and nasty butter and clabbered milk, and then just pour that all into their lab drawer, or pour it into their backpack, or pour it into their seats of a car. You name it. Just do whatever you want to do, and don't tell anybody about it. That's an easy way to get back at an ex or someone that you don't like. So just don't do it to me, though. I don't have anything to... I gave you the hints. Don't think that you can take your revenge out on me on a grade that you don't like. You know, I'm here for you, right? I'm your friend. I'm not your enemy. So here is a reaction that will take an acyl halide, react it with water in a nucleophilic acyl substitution reaction to give you a carboxylic acid. Folks, did you follow that sentence? Because if so, we are talking organic. You are learning organic. You're getting more familiar with organic, so you're making progress. Don't lose out on me now. I know it's at the end of the semester, but don't blink out on me now. We got a long way to go. A long, long way to go. All right, so let me clear this off, and we'll do another example. So let's say here I've got a ring, and that ring, I'm not going to make it a benzene. There's no double bonds. There's no delocalization in that at all. And then off of this ring is a carbon double bond O with yet another chlorine. And then let's react this with CH3NH2. Okay, so what happens here? Well, Tracy, you told us that we just have to learn a mechanism, and that's all that we can do, and we can answer all the questions that we ever need to know if we just learn the mechanism, right? Well, yeah, pretty much. So if I take a look at the CH3NH2, this is a CH3 connected to a nitrogen that has a hydrogen, and that has a hydrogen. That nitrogen has 3 bonds and a free set of electrons. We learned that in Chemistry 251. Very first chapter, very first lecture. There you go. That's the way nitrogen comes to us most of the time in organic. Just like oxygen with 2 pairs, nitrogen typically has 1 pair. Okay, we know the negative source. This negative source is at the nitrogen. That is my nucleophile. The nucleophile is going to come in, look for something positive. What does it find? It finds that poor little carbon in the acyl group. Well, that carbon's partially positive because that oxygen's electronegative, and that oxygen sucks those electrons up. And then the oxygen says, oops, sorry, my mistake, and it shoves them back down. And then that chlorine says, okay, fine, what do I do here? I've got to look at which one's prettier. So it looks at this group and it sees an N. An N. I mean, I know it's not an NH2, but if I remove a hydrogen like we've been doing with all the rest of them, the H and the OH, the H and the alcohols, we've been removing a hydrogen every single time. What it ends up with is a nitrogen with not 2 hydrogens, but a hydrogen and a methyl group. And that's the same kind of deal. It's still a nitrogen. It's still an amine compound. It's still an amine-related cousin. That's all that matters here. I mean, if the real thing's pretty, then the whole family's probably pretty too. The brothers, the sisters, the cousins, and everything else, right? You would hope. Maybe they got good genes in the family. So this nitrogen is regarded as an amine. That amine is going to attack the carbon of the acyl group. The carbon shoves the electrons toward the electronegative oxygen. The electronegative oxygen cannot take the extra charge. It shoves those electrons down, reforming the double bond of the acyl group. And then that carbon looks at this chlorine and it decides to make the chlorine leave because it serves as a very good leaving group. The chlorine leaves, goes off very happy on its own, doesn't need a relationship, Mr. Mrs. Independent right there. And then what we have here is a carbon that has formed a new bond, and that new bond momentarily is a nitrogen with a methyl group and a hydrogen and a hydrogen. That is what it brings to the table. It brings all of it, just like oxygen did with water, just like oxygen did with the alcohol. It brought it all in the beginning. But look, nitrogen's got 4 bonds. It only wants 3 and a pair of electrons. So right now it's positive, just like oxygen behaved. There's no difference in the story so far. So that nitrogen, as you expect, well, this is acidic at this point. It's a protonated amine. And we know pKa's of protonated amines are very low. Again, that was Chemistry 251. So if this protonated amine turns acidic, well, that means that it's going to give off a hydrogen, and that will get rid of the positive charge, and this is what we have left, an NH with a CH3 group. So now nitrogen's pretty stable, 3 bonds, which is typically what it already has or wants, and a free set of electrons in addition to that. Now, if I take a look at this group and I take a look at the group before, let's label the functional groups. So here, C double bond OCl, we know that's an acyl chloride. So I can at least get that point onto the test. And then here, we get this molecule with a C double bond O and a nitrogen on it. So the C double bond ON, well, this is an amide that I have formed. That's great. Good for you. That is an amide that has formed at this point. Okay. Well, what about naming? I didn't name the other rings. Let's name these rings, right? And when we name the ring structures, it seems that that's always the trickiest. This is not a benzene, so I can't call this benzyl chloride or anything like that, okay? So we have to go back to the old original IUPAC rules. It looks a little awkward. It's always the problem area that people have, but you name the ring as a whole. And this ring is called cyclohexane. So there's cyclohexane. Then we name the C double bond O piece, which is carbonyl. And then we add on the halogen, which is chloride. So we have taken cyclohexane, carbonyl chloride, And we have added here CH3, which is methyl, and NH2, which is amine. This was a nomenclature rule that was introduced in Chemistry 251, and you should have been able to name that at this point. So again, a review, but an extensive review going all the way back to really the first 1 or 2 lectures in Chem 251. So I'm taking cyclohexane carbonyl chloride, I'm reacting that with methylamine, a nucleophilic acyl substitution reaction is going to happen. The methylamine serves as the nucleophile. It attacks the carbon of the carbonyl. The double bond reforms. The carbon makes chlorine leave as a leaving group, allowing the methylamine to serve as the substituted group to go on to the molecule. What we end up here at the very end, well, we can name this as well. This is an amine. So the way that we name amines, we name the thing on the nitrogen first, very similar to the way we do oxygen. So that CH3 is a methyl. But because it's directly attached to the nitrogen, I put a N in front of it. That way, you as a reader or as an interpreter could look at this and say, oh, that methyl group is on the N group because he wrote N in front of methyl. So that is attached to the nitrogen. Okay, well, that's good. N-methyl. And then this is the name of the ring that is on the amide group. So that longest carbon chain, which is the name of the ring, yet again, is cyclohexane. I do the whole thing. The C double bond O is still the carbo, but it's not the carbonyl, because that's what we would name it if it was an acyl chloride as above. This has a different ending. So what we end up here with is a carboxamide. And again, we talked about that when we reviewed the nomenclature of the amides and the amines a couple of videos back. So cyclohexane, carbonyl chloride, reacts with methylamine in a nucleophilic acyl substitution reaction to produce N-methyl cyclohexane carboxamide. And there's the structure for the product. Folks, again, it's piecing all of these puzzles together into one big organic picture. And that seems to be the problem that people have. But once they get over that hump, once they feel comfortable doing that type of thing, then it will slowly start to make more and more sense. And then a light bulb will go off. Ding, 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 ding. And then you kind of coast from that point on. It's just trying to get that light bulb to go off first. Now, before I go to the next example problem, I want to discuss a little thing about amines. Very often with the amines, we really like to mess with the stoichiometry of the problem. And in this case, it is not a one-to-one. What we do is we double up. We double up on the amine that we're using as a reagent. And here's the reason. If we don't double up, look at what happens here. You should be able to answer this question without even me telling you what's going to happen. Look at the leaving group that goes on here. This is a chloro group that's a leaving group. All right, so pew, off it goes. Everybody forgets about chlorine. I mean, just the forgotten ugly thing. Poor thing. I feel sorry for it. And then look at what's happened here. That nitrogen brought the extra hydrogen to the picture, and it pew, off to the road as well. And then that hydrogen goes off, and it makes H+. And the H+ and the Cl- might see each other and madly fall in love. And then if they do, this kind of is regarded as HCl. So this is generating an acidic environment. Well, what's the basics of general chemistry? This is not organic anymore. This is just basic chemistry. Look, we have a amine, or in this case, an amide, and the amide is a base. And we have generated HCl, and this HCl has been generated as a byproduct from the reaction, so it's generated an acid. And a acid and a base will react again, and it could completely destroy this product. It is no longer the product anymore. It can almost just revert back on itself. We don't want that to happen. What would be the purpose in making this reaction go forward and make the product only for that product to turn around and react with the byproducts to revert back and go back to the starting place? That's silly. That's stupid. We don't want to do that. So what we do is that we double the quantity of the amines for that reason. And by doubling the quantity, we will have extra CH3NH2 out here that is left over. That does not get used in the reaction to produce that product. It is extra reagent. And the purpose of that extra reagent is to lurk like Jaws, boom, 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 boom. And then it will see the acid and pew, and there goes the bloody water. It kills the acid out of the flask, and that's what we want. We do not want that acid around. So we sacrifice a little bit of the extra methylamine in this case to neutralize the acid that is getting generated from this reaction, so that way that acid doesn't go back and attack the base, which is the major product that we're forming from this reaction. Very important, and almost every single time when we dabble into the world of amines, we are doubling that quantity for that specific reason. All right? So let's take a look at another example. Let's take CH3, C double bond O, and in this case Br, not Cl. It seems like we've used Cl all the time, so I'll use Br here. And then we're going to react this with just simple little o NH2, all right? Or NH3 maybe. Doesn't really matter. I don't care. It both happens the same way. Okay, so if this goes forward, then we have an issue here, and that issue is that the organic knows that that amine is Miss America of the bunch. So it will kick that chlorine off, and there's our product that we form if this was just full-blown NH2 minus, just NH2 minus. So the bromine gets kicked off in this case, and this NH2 is going to come in, and this NH2 doesn't really have a hydrogen to kick off. So here we're kind of safe, right? So probably what's happened here is that in order to get this negative NH2, we've had to bring something else into the picture. It wasn't hydrogen, but it was probably some counter ion that allowed this to happen. So we kind of saw this a little bit in the acid-base reactions when I kind of told you, you don't just get NH2 out of a bottle. You just don't order NH2 minus, right? I mean, that whole thing, that whole concept, you just can't do it. It's got to come along with something else. So here we're kind of okay. There's not a hydrogen for that nitrogen to give off. Because there's not an extra hydrogen to get off, we never really form the acid, and we don't really need 2 rounds of NH2 there. But what if this was an NH3? That is where the story changes a little bit. And that is where we have to be careful, because now what goes on is that NH3 comes onto the acyl group, and that NH3 brings together the whole party. And that nitrogen now is positive at this point. It's got too many bonds. There's a total of 4, just like before. And that nitrogen decides to get rid of that hydrogen so it can get rid of that positive charge. And we have this extra little hydrogen that can, hey, bromine, I know you're ugly, but I'll fall madly in love with you if you just take me home. And bromine says, okay, let's go. So now we've generated HBr, which is hydrobromic acid. So we do have an acidic content at this point, and at this moment is when we realize, oh, we've got to completely destroy that acid out, because this is a base. It is an amide. So that base and the acid will react unless I throw in double the amount of ammonia to make that stop. So that way extra ammonia can happen here on the back end, and that extra ammonia can cross out that HBr that's getting generated throughout the reaction. So NH3 serves 2 purposes. These amines, they will serve two purposes almost every single time when we need to use them. One, they will be the reagent to produce the product. And two, they will be the reagent that will also destroy the byproducts, especially if they are acidic in nature. All right, so that's where this video will stop. In the next video, we'll keep doing example problems. We'll keep looking at this kind of mechanism, get more comfortable with it. And then I think that you'll see that these reactions get easier and easier the more we do them.